Welcome to the online meeting of the Working Group 2 of the Attochem Cost Action. As you know, the main objective of this action is to design attosecond light pulses and attosecond control strategies that can efficiently be used to induce specific charge migration dynamics in molecules. This action brings together chemists, physicists, experimentalists, and theoreticians from more than 26 countries, facilitating their collaboration. Unfortunately, in the last year, we had to rely mostly on virtual online collaboration. This new situation was slightly easier for the Working Group 2, which handles the theoretical and computational part of the Attochem actions activity. As far as I know, the collaboration between our research groups didn't stop. However, it's a pity that we did not have much opportunity of STSMs and on-site visits, face-to-face discussion. This virtual meeting of the Working Group 2 members tries to fill the gap in the personal contacts. We will have the opportunity to know each other's research methods, new ideas, and interesting results, almost as in case of an on-site meeting. However, we will miss the conference dinner. Finally, I remind you some technical issues. The audience is kindly asked to keep the microphones muted during the talks. After the talk, if you want to ask questions, please use the raise hands button either from reactions menu or from the participants list. After each session, you will have the opportunity to discuss with the speakers of the session using the Zoom links available in the program of the meeting's webpage. Most of the talks I streamed also on YouTube for a larger public, so I greet also the audience on that channel. Finally, enjoy the meeting. Now I ask Fernando Martin, the chair of the Attochem Cost Action, to say a few words. He will chair also the first session of the meeting. Fernando, please.
Thank you very much, Ladislao, for the introduction. Well, first of all, I want to thank Ladislao and his team for organizing this meeting and for designing the program of this meeting. I think this is something very important and will help us to keep alive the action during these hard times. Well, as Ladislao has said, the purpose of our Attochem network is to study how attosecond science can be used to study problems of chemical interest. And this includes both experimentalists and theoreticians. But as theoreticians, I think we have the responsibility to guide experimentalists and to help them to interpret their very complicated measurements. And this meeting is devoted mainly to present theoretical tools that have been developed recently in the framework of our action to meet this goal. I'd like to remind you that the aim of the cost action is to encourage mobility and contacts between researchers. Unfortunately, mobility nowadays is not an easy thing, and but I'd like to remember anyway that we have at the disposal of the cost participants our short-term scientific missions that allow to spend some time in a different laboratory just to learn new things, just to go on with a collaboration or whatever you want. I think that this tool is there, and although it cannot be used as massively as in normal circumstances, still I think that it could be very valuable for some of you. So I encourage you to consider this possibility, especially in the forthcoming months where the situation all around Europe seems to improve. And the other important aspect of this cost action is to organize meetings, to encourage contacts between different researchers. And so far, I think we are doing very well. We had already our first annual meeting in last September that was held online. And we are now having few working group meetings on more specialized topics as this one. So finally, I'd like to tell you that if you want to benefit from all these tools that our Attochem Action puts at your disposal, you should register in the Attochem website. So please, if you have not done it yet, please do it. Go to the Attochem website, fill your data, and that's it. And then you will be informed about all the developments of the action, and you will be able to apply for whatever you think is useful for your research. So please do it. And I extend this invitation to the speakers and chairs of this meeting. It takes only a couple of minutes to fill the registration form. And with this, I am done. I reiterate my thanks to Ladislao and his team, who have worked very hard to organize this meeting. And I hope that this meeting will be a successful one for all of you. Thank you.
Thank you very much, Fernando. I think you can continue with the first session.
Okay, well, it's not yet 10, so maybe we can wait 2 or 3 minutes in case. But what I can do in the meantime is just to remind the audience a few rules that you already mentioned, but I think they are very important in case somebody logged in later. So during the session, please turn off your microphones and cameras. That is very, very important to avoid any disturbance during the talks. Also, this will be held in the normal way. I mean, the speakers will have time to deliver their presentations. And after that, there will be time for questions. The total time given to each speaker is 40 minutes. And so the talk should be around 35 minutes. And then we should have like 5 minutes for questions. It could be a longer time for questions if you want. And the way to ask questions at the end of the talks is by raising your virtual hands in the Zoom. This you can do it in case you are not familiar with Zoom. You can do it depending on the version of Zoom you have, but in some versions there is a link in the bottom of your screen that is called reactions, and you click there, you will see different icons, and one of them is a raising hand. So please click this icon to raise your hand whenever you want to ask questions, and I will, at the end of the talk, I will call you to open your microphone and camera to ask the question. And in other versions of Zoom, the link is not in the bottom, it's just in the list of participants. So you open the list of participants, and then at the bottom of this list of participants, you may have a link to raise your hand. So please follow this way, otherwise it will be complicated to develop the session in a normal way. So with this, I think we are just in time. So it's my pleasure to chair this first session of the Working Group 2 meeting. We have a very attractive session with Eva Brezinova, Loic Hubert-Doriol, and Elke Faschauer. I pass the floor to Eva, who is going to speak about the time-dependent two-particle reduced density matrix method.
Thank you very much, Fernando. I hope you can hear me.
Yes, very well.
Very good. So first, I would like to thank the organizers for giving me the opportunity to talk about our research here. And I will start sharing my screen. I hope you can see it now in presentation mode.
Yes, yes, we can.
Great. Okay. So, yeah, it's a great pleasure to talk here, although I have to admit I'm very much looking forward to the next work group meeting where we hopefully can meet in person. So, as Fernando already mentioned, my talk is about the time-dependent two-particle reduced density matrix method, and a disadvantage of this method is it's a very long name, so I will use the abbreviation TD2RDM. It's much easier to be remembered. And I will show you what this theory is about, and I will show you our first applications of this theory. We are generally interested in non-equilibrium dynamics of many-body systems. So a prototypical example is electrons, for example, in an atom, or maybe also later in a molecule, driven by a strong or an ultra-short laser pulse. This is the prototypical platform we want to use our theory for. And obviously you all know that if one wants to describe such a thing theoretically, since this is a strongly driven system beyond linear response, one has to use an explicitly time-dependent Hamiltonian. And this Hamiltonian typically has the form of a sum over one-body operators and the pairwise interactions. And then we, of course, write down the time-dependent Schrödinger equation, and it doesn't cost much to realize that a direct solution is not possible except for very small systems. And the reason is the exponential scaling of the numerical effort we have, if we want to really solve the full Schrödinger equation. So there are several methods already available to address these questions, but they are very different when it comes to their assessment regarding numerical effort and accuracy. So I have grouped them into two groups and just picked one representative. Of course, there are others within each group. So one representative is MCTDHF, which is a wave function-based ab initio method. So it explicitly uses a wave function that is then propagated. And it can be made very, very accurate, but of course the numerical effort is also very high because you still have this exponential scaling. On the other hand, there are methods that are based on reduced objects, and the most prominent example I would say is time-dependent density functional theory, which is a density-based method. Here the accuracy is quite limited. It depends a little bit on the system and also on the functionals that you use. But overall, the accuracy is not very well controlled. But the numerical effort is very small. And therefore, it's also applicable to large and extended systems, like even solids. But we thought there is a huge gap in between. And our aim was to find something that is also polynomially scaling, but more accurate. So we wanted to have a theory that is polynomially scaling, but much more accurate than TDDFT, and maybe close to as accurate as a wave function-based method like MCTDHF. And I will show you in the following whether we succeeded or not to find such a theory. So the overview is, I will introduce to you the method, and then I will show you first application. So let me start with that. The reduced object we are using is the two-particle reduced density matrix. Since we want to avoid this exponential scaling, we have to use some reduced object, and we decided to pick the two-particle reduced density matrix for several reasons. One of the reasons is that two-particle correlations are then exactly incorporated. And you get this two-particle reduced density matrix if you take your full wave function and trace out all but two particles. So imagine you just have two electrons, then of course this would be the full information that you can even have. That would be the full density matrix of the system. And then the dynamics would be described by this Hamiltonian consisting of, I just tried to turn off. Do you see my mouse, or do I need to have a laser pointer?
I see it. I see it.
Okay, great. Then I will just use my mouse. So the two-particle Hamiltonian consists of two one-body operators naturally and the pair interaction. And if we would have just this pair, then the equation of motion would be just the von Neumann equation, which is given by this formula here. But of course, we want to go beyond just 2 electrons. So let's say we have a quite large number of electrons. And of course, each pair interacts with its environment. So this electron interacts with the other one and any other electron. And by this construction already, you see that if we want to now describe the dynamics of the 2-particular use density matrix, something is missing here in this equation of motion. And this something is the 3-particular use density matrix, because from this construction, we can already see that 3-particle correlations are important for the dynamics of pairs. So this is the part that has been missing before. As such, this is still an exact equation of motion. This equation of motion is one element of the so-called Bogoliubov-Born-Green-Kirkwood-Yvon hierarchy. This is a coupled hierarchy. So the first element describes the dynamics of the 1-particular use density matrix. The second element is the one we want to consider now, and so on and so forth. And it's only closed for Q, so Q number of particles that you consider equal to n, because it is coupled. So if we want to restrict ourselves just to the second element, we have to somehow approximate the 3-particular use density matrix by a closure. And the rest of the talk will be how to do exactly that. So to find a suitable reconstruction functional of the 3-particular use density matrix, and then plugging that in is what the time-dependent 2-particular use density matrix will be about. So just to mention, I'm afraid the last line you cannot see because it is somehow covered by my task line, but just I will verbalize it. So the scaling of this method is to the power of 5 if we use a grid basis, or to the power of 7 if we use an orbital basis, and linear in time. So we have a polynomial scaling with this theory. So what are the ingredients for a successful approximation or a successful approximate closure? You need to have an accurate reconstruction. You have to make sure that constants of motion are really conserved during time evolution. And then there is one thing we will have to deal with, which is called the n-representability problem, and I will talk about it later. Just to give you a feeling about the 2-particular use density matrix, I would like to show you a little bit what how this 2-particular use density matrix looks for a prototypical system like a beryllium atom. So let's just look at its structural properties. So this is the 2-particular use density matrix. Well, it's not a matrix anymore because we just have used the diagonal. So it's a 2-particle distribution as a function of the 2 radial components. And what you can already see here is the trace of the 1s shell, which is occupied by 2 electrons. This is a combination of 1s and 2s. And it is quite strongly enhanced because the number of pairs you can have is double compared to the 1s shell or the 2s shell, so along the diagonal, where you can just have 1 pair. So up, down, along the diagonal, 1s and 2s. And if you have strongly different radii and you combine 1s and 2s, you have 4 pairs altogether. So therefore, these wings are enhanced. So this is the 1s shell, and this is the 2s shell with its pairs. This is the full 2-particle distribution. But I can show you now explicitly 2-particle correlations. And how do I get them? I can always separate this 2-particle distribution into one component. This is the Hartree-Fock component that I would get if I had independent particles that are non-interacting. So just coming from a Slater determinant, one can construct this component from the 1-particular use density matrix, plus something that cannot be constructed from the 1-particular use density matrix. And this is exactly the 2-particle cumulant that measures correlations. And what you can immediately see here is the so-called correlation hole. So the particles do not like to sit on the same shell. The 1s shell here and the 2s shell here get a reduced two-particle distribution. So I have already mentioned that if we have the two-particle reduced density matrix at disposal, two-particle correlations are fully incorporated. And I will now explain to you this in a little bit more pictorial way by a diagrammatic expansion. And I will use diagrams that resemble very much those that are used for Green's functions. But please bear in mind that these are not Green's functions, but density matrices, so something like an equal time limit of a Green's function. But because people are more familiar to these arrows from Green's function theories, I just have used the same pictures here. So this is what is all incorporated in the two-particle reduced density matrix, namely, again, this component that is just an antisymmetrized product of two one-particle reduced density matrices, and this is exactly this Hartree-Fock component we had before, and then again here this cumulant. And this cumulant, these two-particle correlations, are fully included in the two-particle reduced density matrix method if we use the 2RDM as the fundamental object. But as I already mentioned, for a closure, we also need the three-particle reduced density matrix. So some components, again, are reconstructible by reduced objects. So this is, again, the, let's say, trivial part, which is an antisymmetrized product of three one-particle reduced density matrices. And again, this is the Hartree-Fock component. But then there is one component we can construct directly if we have the cumulant at disposal, the two-particle cumulant. So these are processes where two particles are correlated and the other one is not correlated. And this one can explicitly write down as an antisymmetrized product of the two-particle cumulant and a one-particle reduced density matrix for the third particle. And then there is something that is not reconstructible a priori from the two-particle reduced density matrix, namely the three-particle cumulant that measures real three-particle correlations. So one approximation known from literature is just neglecting these three-particle correlations altogether and use this as a reconstruction functional for the three-particle reduced density matrix. This is then called the Valdemoro reconstruction. We had the experience that this is not a sufficiently good reconstruction, and we had to go beyond that. So we had to approximate this three-particle cumulant, and we did that by this sequence of two-particle correlations that can also be written down using the two-particle cumulant, and this is known in literature as the Nakatsuchi-Yasuda reconstruction. So this is the reconstruction that we have ultimately used. Now, one thing that is very important and that has hindered previous attempts of establishing or using the time-dependent two-particle reduced density matrix is the following observation. Of course, conserved quantities should be conserved during time propagation. So if you have a Hamiltonian that is not explicitly time-dependent, energy should be conserved, for example. But also, for example, spin degrees of freedom. If you drive your atom with a laser, spin is a conserved quantity. And also, the hierarchy of these equations should be consistent. So if we take our two-particle reduced density matrix, the equation of motion for it, and we trace out one particle, we should consistently arrive at the correct equation of motion for the one-particle reduced density matrix. So let's see whether this is fulfilled by our reconstruction function. So for example, energy conservation, but also this consistency between the hierarchies, between the first and the second, requires that the three-particle reduced density matrix correctly contracts upon tracing out the third particle to the two-particle reuse density matrix. So any reconstruction functional we use here should have this property. And of course, this is trivially fulfilled for the exact 3-RDM, so three-particle reuse density matrix, but it is not fulfilled by any of the so far mentioned reconstructions. And we came up with a solution for that problem, namely by calculating this defect, that is just the difference between the trace and the full two-particle reuse density matrix. And then it turns out one can correct any reconstruction functional by a component of the three-particle reuse density matrix that exactly contains this defect. So this is a component that has a vanishing cumulant, but can be constructed from its contractions, and therefore produces a three-particle reuse density matrix that exactly has these correct contraction properties. So we use here the unitary decomposition, and if you want to know more of this technical detail, I can discuss it with you later. But just let me show you how important this contraction consistency is. So for that, we use as a benchmark method MCTDHF, and we have propagated beryllium in a quite strong laser field driven by an IR laser field of quite high intensity. And what we do here is just to benchmark how important contraction consistency is for this reconstruction. We calculate in parallel MCTDHF, and for each time step, we compute the correct three-particle reuse density matrix and the reconstructed one, including this contraction consistency. And just look at the reconstruction error. So the difference between the full three-particle reuse density matrix and the reconstructed one. And the two curves show you with and without contraction consistency. So this is the reconstruction error. We have just used the Hilbert-Schmidt norm for that as a function of time. And this is this Nakatsuji-Yasuda reconstruction functional. So without contraction consistency, this is the error of it. And now if we apply contraction consistency, you see that the error decreases by an order of magnitude. So this was very important for this closure of the equations of motion. So overall, the reconstruction is improved, and this is true for any, or applicable for any reconstruction functional. Now to this n-representability problem that also hindered previous attempts. And just to give you a perspective on that, I will now talk a little bit about ground state problems, because the two-particle reuse density matrix theory has been first established for ground state problems in quantum chemistry. It's quite widely used already. And the problem of n-representability in principle accompanies this method since the 50s. So now I will just talk about ground state problems and then also compare to DFT, that you get a feeling for this n-representability problem. And then I will show you how we had to deal with it in this time-dependent framework. So let's talk about a variational ansatz for the two-particle reuse density matrix for calculating the ground state of a system. Now you have to know that the energy of any system is an exact functional of the two-particle reuse density matrix. This is different for densities, because there the energy functional is not known. But for the two-particle reuse density matrix, the energy functional is exactly known. And the reason is that the Hamiltonians we use contain only pairwise interactions, and therefore the energy functional is an exactly known functional of the two-particle reuse density matrix. So already in the 50s, people realized that and said, okay, then let's use this known energy functional and do a variational ansatz to determine the ground state energy of any quantum system. And they used an ansatz for the two-particle reduced density matrix that was very reasonable. Of course, the reduced density, any reduced density matrix has to be Hermitian. And since we have fermions, it has to be antisymmetric. It has to be positive semi-definite. So the eigenvalues have to be larger or equal 0. And with this ansatz, people tried by a variational approach to determine the ground state of multi-electron systems. So the idea was we start with a test two-particle reduced density matrix, and then iteratively we minimize the energy and obtain then the correct two-particle reduced density matrix of the ground state. But what people had to figure out is that the energy they obtain is much smaller than the exact ground state. Now, that might surprise you, because if you remember how variational methods usually work, you obtain usually an upper bound for the energy. And the reason for that is that usually the variational approach is done within wave functions. So explicitly in the Hilbert space. And there, of course, the well-defined minimum is just the ground state wave function. But here it seems by minimizing this energy just by these restrictions, we have left the Hilbert space, because otherwise we would never reach an energy that is smaller than the real ground state energy. So this is what the n-representability problem is about. These conditions that I have mentioned before, Hermitian, antisymmetric, positive, semi-definite, are not enough to guarantee the correct quantum statistics. That is, to guarantee that we have probed only the two-particle reduced density matrices to which actually a fermionic wave function belongs. So just to compare the two methods, the two RDM and a density functional theory, since I guess that some of you are very familiar with density functional theory, I want to just show the similarities but also the differences. So as I have mentioned already, the energy is a non-functional of the two RDM. This is not the case for the energy functional in DFT. So this is one advantage of the two RDM, but one disadvantage of DFT. But now comes the n-representability problem. The n-representability problem for the two RDM is solved. I've put that under quotation marks because it's only implicitly solved. There is a constructive method to find all necessary conditions, but unluckily for us, there is an infinite number of them. And in any real application, you of course have to restrict yourself to a small number of necessary conditions that can be incorporated. And incorporating these few necessary conditions, this is what is then called purification. For densities, the ensemble and representability problem is solved. I want to point out here the word ensemble, that is the mapping between a density matrix and the density, because it just requires that the eigenvalues of the one particle reduced density matrix must be within 0 and 1. Now, what about this mapping between wave functions and the two particle reduced density matrix? There is a theorem, it's called Rossina's theorem for the ground state, that there is a bijective mapping between the wave function of the ground state and the two particle reduced density matrix for the ground state. And this is again a little bit different for the density, because there is not a bijective mapping. There is one wave function that maps to the one particle reduced density matrix. And if I know the Hamiltonian, I can say this is exactly the wave function that I'm interested in. But there are other wave functions. For example, Slater determinants can be constructed that map exactly to the same one particle reduced density matrix or density. And this is in fact used in the Kohn-Sham ansatz. So there is no contradiction to the Hohenberg-Kohn theorem. So I mentioned Rossina's theorem already. There is this bijective mapping between the many-body wave function and the two particle reduced density matrix. So in principle, an exact reconstruction functional should exist due to this bijective mapping. we want to now perform a time-dependent propagation of the two-particle reduced density matrix. So it would be good to know whether this bijective mapping and therefore also an existence of a reconstruction functional is in principle guaranteed by something like an equivalent of the Runge-Gross theorem for the two-particle reduced density matrix. But this is an unsolved problem. So there, an equivalent of the Runge-Gross theorem has not been found yet. But let's not get stuck by some not yet solved existence theorems and just move on and look what happens. Unfortunately, this n-representability problem tends to jump into our faces as soon as we try to propagate the two-particle reduced density matrix with a reconstruction functional of the three-particle reduced density matrix. I have to say it's not always the case. I will show you later applications where we did not have this problem because the reconstruction functional was so accurate for that specific problem. But if it is not accurate enough, we face the following. So one necessary condition is that the probability to find a pair in some two-particle state always has to be larger than 0. So the positive semi-definiteness of the two-particle reduced density matrix has to be guaranteed, and the eigenvalues have to be larger than 0. But sometimes what we see is if we just propagate, what I show you here are the eigenvalues of the two-particle reduced density matrix as a function of time, and this was again beryllium, driven by a strong IR field. And I plot you here the largest and the smallest eigenvalue. And at some point you can see that the largest eigenvalue gets infinite and the smallest eigenvalue gets negative and negative infinite. And at this point, when this eigenvalue becomes sufficiently negative, the equations of motion are simply unstable. And this instability is due to this violation of n-representability. But we managed to cure this problem by the following. Namely, what we do is, and empirically we have realized that it's enough to incorporate just two necessary n-representability conditions, namely the positive semi-definiteness of the 2-RDM and the 2-hole RDM. So the pictorial picture we have is that if I imagine the space of the two-particle reduced density matrices that belong to a wave function as this space, it definitely looks different, but just for the sake of having a picture. And this would be the exact dynamics. The reconstructed or approximate dynamics sometimes moves us above this space or beyond this space. And by applying on the fly this purification where we guarantee that the 2-RDM and the 2-hole RDM become positive semi-definite again, it brings us close again to this exact dynamics. And with that, we can stabilize the equations of motion for a sufficiently long time. So that brings me to the applications. And what I will talk about are applications to high harmonic generation. So as you all know, high harmonic generation is a strong field effect where in the 80s it has been observed that the response of an atom to a strong field gives rise to this plateau of photonic energies that come out of this target that cannot be explained by perturbative ansatz. And the explanation that is very intuitive is the 3-step model that relies on 3 steps: on ionization, laser acceleration, and then radiative recombination. In our numerics, I will now show you explicitly results for neon. So neon driven by a strong IR field of 10 to the power 15 and 800 nanometer wavelength. So for us in our numerics, the 3-step model is not explicitly obvious. For us, it's just a shaking electron density. I will show you this slide again, that you see this electron density shaking, and this accelerated electron density produces then this radiation, and we calculate this radiation just using the well-known Larmor formula. And in the following, I will now show you the results for neon, so the high harmonics, the yield of high harmonics as a function of the harmonic order. And I will compare the the time-dependent two-particle reduced density matrix method with MCTDHF, which we have used as benchmark. So in this theory was accurate in the sense that we had enough orbitals that it was numerically converged. So these are kind of the exact results. And then I will compare to time-dependent Hartree-Fock and time-dependent DFT. The time-dependent DFT version we have used was LDA with the VWN correlation function. And this is the high harmonic spectrum. So there is a gray curve, this is time-dependent Hartree-Fock, a blue curve, this is time-dependent DFT. MCTDHF you almost cannot see because it is practically exactly covered by the time-dependent 2RDM method. So our method is really very accurate, at least for these systems. But let's try to understand a little bit more where these discrepancies come from, especially those of TDDFT and TDHF. And for that, we go back actually to the three-step model because it can guide numerical results or the interpretation of numerical results. So in this three-step model, the harmonic yield is proportional to this ionization rate. And then we have these classical trajectories that then recombine back with the parent atom and the recombination probability, which we have approximated by the ground state occupation probability. And if you look at these observables, the ionization rate as a function of time, what you see here below are the relevant classical trajectories, then it becomes obvious that TDDFT largely overestimates ionization and TDHF underestimates it. And for the recombination probability, it's the other way around, but the recombination probability is very large. So in principle, almost 1 for both, or for all the applied theories. So the most important effect here is actually the ionization rate, and the ionization rate being strongly TDDFT predicts a much stronger ionization rate than all other theories, and therefore TDDFT is so much off here. So let's discuss maybe also a case where we looked at beryllium, because there also the effect of two-particle ionization comes into play. And again, the TDDFT and TDHF approaches are practically completely off, and MCTDHF and time-dependent 2RDM fit extremely well together. So here one can understand this overestimating the plateau region again by looking at the ionization rate and the ground state or the recombination probability. And the trend is exactly the trend that you see here, namely that both overestimate the plateau can be explained by both overestimating the ionization rate, but also the recombination probability. But one can do here more. So let's look at this spectrum, the time-dependent 2RDM spectrum, and I will just show you this because MCTDHF looks in principle exactly similar, and then compare to single active electron calculations. And I have two of them. I have one single active electron calculation where I have used an ionization potential that corresponds to beryllium, and one that corresponds to beryllium plus. So ultimately, that would be an electron that comes back to a parent atom where actually 2 electrons are missing. And here in this region, the single active electron approximation for beryllium plus fits very well, whereas here it's opposite. The single active electron calculation just for beryllium fits very well. So how can we explain that? And the explanation is simply the following, that in this region, the electrons have been ionized at the largest laser peak, and then they recombine through this smaller following laser peak. So therefore they land just between the 10th and the 30th harmonics. But if you look at the two-particle ionization probability, you can really see that in this region, it is strongly enhanced. So therefore, this peak really comes from the electron recombining with a beryllium 2+ atom and not just a beryllium plus atom. And our theory can nicely reproduce all of that. So one single active electron calculation will not give you the correct answer, but our theory can really deal both with single as well as two-particle ionizations. So with that, I would like to conclude. I have shown you that we have developed a new accurate time-dependent quantum many-body approach that is called time-dependent two-particle reduced density matrix theory. It is suitable for the non-perturbative treatment of strong field physics, and it has a polynomial scaling with particle number. And what we want to do next is further develop this theory, because one can do even more. One can use even finer reconstruction functionals. Also with the purification, we want to develop further approaches that make it maybe more efficient and more accurate. And our final goal will definitely be to apply this to larger systems, not only atoms, but maybe even extended systems, and investigate all the correlation effects that partly have been neglected in strong field and attosecond physics. And with that, I would like to thank my collaborators, especially Fabian Lackner and Stefan Donzer, two students that worked on this theory together with me, Joachim Burgdorfer and Takeshi Sato and Kenichi Ishikawa, who have given us their MCTDHF code at disposal, with which we have calculated all the benchmarks. And I would like to end by thanking you for your attention.
Thank you very much, Eva, for this very interesting talk. So we have now time for questions. So I see already a hand. Elke Faschauer, you can ask your question.
Hi, Eva, and thank you for the very nice talk. And I guess I applaud to you on behalf of everybody else. Could you go back to the slide that you called construction consistency?
Yeah, so there, yeah.
That's the next one. This one. The two curves that you have, they look like they follow the same path. So do you think there is a systematic error that you have in these two approximations? And do you have an idea what that is?
So that's a very good observation. It also struck us, of course, that these curves just look shifted. And we don't have a good answer for your question, actually. So what we observe is that what we do in this contraction consistency is, maybe I should maybe talk a little bit more what is part of this contraction consistency. So what we use is a so-called unitary decomposition. And this unitary decomposition tells you that every matrix that you have can be divided into one part that has non-vanishing traces and one part that is completely trace-free. And this part that has non-vanishing traces can be exactly reconstructed. There is a formula for that by the contractions of this matrix. So what is left is the part that has no contractions. And what we obviously in our reconstruction functionals miss, even with contraction consistency, is the part of the three-particle cumulant that has no traces. So the three-particle cumulant has a part that is not trace-free, that we incorporate, but it has also one part that is traceless. And this is the error. And it also strikes us, but we don't have a good answer for that, why this traceless, the part of the three-particle cumulant that has non-vanishing traces just leads to an overall almost so an overall, like a factorial reduction of the error. I cannot tell you any mathematical reason why that should be the case. But it's really an empirical observation that this reconstruction error gets reduced by about an order of magnitude or even more. These fluctuations that we see on top of it are almost the same for in both cases.
Okay, thank you.
You're welcome.
I see another hand. Loïc Joubert-Doriol, ask your question.
Yes, thank you. Thank you for the talk. That was very pedagogical. I hope you can hear me well.
Yes.
My question is related to the breaking of the positivity of the matrix that you have. And you were saying that at some point, one eigenvalue becomes negative, and then the whole thing diverges, basically, right?
Mm-hmm.
Do you have any idea of what is the reason for that? I would think about something like a division by 0 or something like that is the case. And then a second question related to that is why not maybe to use an ansatz of like, let's say, the Cholesky decomposition of the matrix instead of the matrix itself to ensure positivity?
Okay, so the instabilities that we see, and this is again a little bit empirical, and we were not the only one that saw it. So it seems that these equations of motion contain a feedback that leads to negative eigenvalues getting more and more negative. So this feedback mechanism is really somehow intrinsically built into these equations as soon as you start to reconstruct your three-particle reduced density matrix. This is such a general observation that there might be, again, some deep mathematical reason for that. We just have empirically, and not just us, but everyone that tries to propagate two-particle reduced density matrix, we have just empirically noticed that any tiny negative eigenvalue of this density matrix gets enhanced. The eigenvalues in principle really directly, so if you write down the equations of motion just for the eigenvalues, they really directly couple only to the part that contains the three-particle cumulant or the three-particle reduced density matrix. And it seems that any tiny error there really enhances itself. So it's a little bit along the lines of the principle of conservation of misery, because if we did not have that problem and if we just could propagate without instabilities, then this would be really much, let's say, it's a little bit, I tried to show this in this comparison between DFT and 2RDM. So in DFT, you have the problem of not knowing your energy functional, but by construction, your equations of motion are stable, because with the Kohn-Sham ansatz, you have made sure that you do not leave the space of unrepresentable densities. But here we have an energy functional that is in principle exactly known, and also we have a reconstruction of the three-particle reduced density matrix, and we incorporate all the correlations. But despite these equations of motion being much more accurate than TD-DFT, probably with any functional that you can come up with, at least in a universal sense, we face the problem that these equations of motion tend to enhance errors when it comes to negative eigenvalues. So one has to do something about preventing these instabilities, and this is really just pushing those eigenvalues again back to 0, and this is what we do. And the other question about the decomposition you mentioned,
yeah. You want me to repeat? Or?
Yeah, please repeat, because I don't know it, so I cannot tell you.
No, the idea would be, like in DFT, you are using a set of electronic states, one particular electronic state, to construct the density matrix, and that ensures that everything is positively defined. Like you don't have negative probabilities. And you could do the same maybe for a matrix, but then somehow the root square of a matrix would be the Cholesky decomposition, right? So you can maybe propagate this Cholesky decomposition and then reconstruct this density matrix when you need it.
Yeah, okay.
And that would ensure the positivity of the matrix.
Yeah, honestly speaking, I haven't thought about that. It's probably a very good idea, and I will have a look at it. Thank you for that comment.
If you, because I developed a method for this, for propagation of such objects. If you want, we can talk about it later, maybe, or I can give you some reference.
Yeah, it would be, I would be very thankful for that.
Okay, well, I think there are probably more questions, but we had to move on. And so you want to discuss these issues in more detail, I invite you to join this meet the speaker session that we'll start just after this session. So I invite now, thank you, Eva, again, for the nice answering the questions. So now I invite Loïc Hubert-Doriol to give his talk about from low energy non-adiabatic dynamics to attochemistry, and he's from University Gustave Eiffel, France.
Okay, thank you for the introduction. I would like to start by thanking the organizers for inviting me. Wait a minute, maybe I will switch to full screen presentation. I would like also to mention that I am in fact replacing Fabien Gatti. Today he couldn't come, but we have a project on attochemistry together, and I will be talking about how I want to extend my knowledge in low energy non-adiabatic dynamics to attochemistry. And so really the target system that I have in mind is, for example, this oligopeptide that I think most of you already know. There was a famous experiment done more than 20 years ago on this system. And upon light pulse excitation, there is ionization of the molecule and subsequent electronic dynamic. Here it's a whole migration over this oligopeptide, and then this hole will localize on a specific position and lead to fragmentation. And the hope is that maybe one day we can control this system by optimizing the initial light pulse and maybe localize the hole in some other position and lead to other fragmentation, and that hopefully would be what we call attochemistry. But I am in fact a bit far from that, as you will see later in the presentation. And I come more from the community of people working on what I call low energy non-adiabatic dynamics, where only few electronic states are involved, the few lowest energy electronic states. And usually I take this example of the retinol isomerization to explain what I've been working on. So here we have two electronic states that are represented, the ground and the first excited state. And this reaction is just isomerization from cis form to trans form. And this is the first step of the division process. So it's quite important for biology. And the process is happening as follows. First, there is excitation, for example, from sunlight. And then the system will evolve on the excited states and reach a geometry that is called conical intersection, where the two electronic states have the same energy. And since the coupling between the electronic states is inversely proportional to the energy difference, then the coupling tends to infinity at conical intersections. And when the wave packet reaches this region, it can de-excite to the ground state without emitting a photon, and then continue and evolve towards the product. So here, a key feature is that there is this object that I call the conical intersection, and maybe most of you are already familiar with that, and it will be a central object in a part of my presentation. So how to run the simulation of such molecular system? Well, we would like to solve the time-dependent Schrödinger equation, so with the nuclear kinetic energy, electronic Hamiltonian, and here maybe a time-dependent term that would account for the light pulse. The first thing we can do to reduce the complexity of this problem is by choosing a well-suited electronic basis. And since we are working on the lowest electronic states, very quickly you can think that maybe the adiabatic states are the best ones because they basically minimize the energy of the electronic states by diagonalizing the electronic Hamiltonian, and then we obtain these states that depend on the nuclear degrees of freedom because this is parameterized here by the nuclear degrees of freedom. And then we project our total wave function on these states, and we obtain then a linear combination of products of adiabatic states and another term that is the nuclear wave function that evolves on each of these electronic states. And this comes in fact from the projection of the total wave function on the adiabatic states. So since we have only 2 electronic states in this process, we can just truncate this sum up to 2, basically. And then we reduced already the problem by a really huge amount in terms of degrees of freedom, because we replaced all the electronic degrees of freedom by only 2 discrete indices, basically. But we are left with all the nuclei, and as you already know, this is called the curse of the dimensionality. Quantum methods scale exponentially, and here, let's say we use a grid with 10 points per dimension. We would need this huge number of points just to represent the wave function, which is completely impossible as for now. So there are different ways around this curse of the dimensionality. There is, for example, the MCTDH method that can be used for the nuclei, and I will talk about that in the second part of my talk. But also we can think about using decomposition of this nuclear wave packet using Gaussians. And the reason why this using Gaussians can in fact work is the following, is that we are interested in processes that are ultra fast, and on this time scale we hope that the nuclear wave packet remains rather localized, and therefore the Gaussian wave packets are well suited to represent such a wave packets. Furthermore, the Gaussians can be parameterized by their the position of their center and a momenta if we make them evolve in time, and therefore they will follow somehow one-dimensional trajectories, each of them. So we are replacing these multi-dimensional grids by a bunch of one-dimensional trajectories, and hopefully those trajectories won't scale, like their number won't scale exponentially. Then we expand our nuclear part in this basis, and we still have to calculate the adiabatic states, but that can be done from electronic structure packages and even on the fly, so we don't need any model here a priori. To obtain the dynamics of, the time-dependent evolution of such an ansatz, we are using the time-dependent variational principle. And here I am using, in fact, the stationary action, where we define such an action here. And when we make it stationary, it leads to this, extra condition. And when we plug our ansatz in this condition, we obtain the equations of motion for all the parameters that appear in our ansatz. So for example, these coefficients and also the parameters. And for example, for the expansion coefficients, the equation of motion is actually quite simple. It looks just like the Schrödinger equation, but for a non-orthonormal basis that is time dependent. So we have these extra terms, but it's quite simple. For the parameters, it can be more complicated, but this can be simplified by just using classical trajectories for the motion of the Gaussian center. And that doesn't spoil the fact that all the approach is really fully quantum at the end, because if we, in the first step, propagate or evolve all these parameters, then in a second step, we can reconstruct all these Gaussians using these trajectories. And we will use this time-dependent basis that if we use a lot of them and we take the limit of an infinite basis set, we would still recover the exact solution for the Schrödinger equation. So when we plug our ansatz with this time-dependent basis, even though it's not optimal, it still gives back a variational approximation to the total molecular wave function. And with this approach, you can really attack problems with very large molecular systems. For example, with the ab initio multiple spawning method, the retinol was modeled here in real time. Also, with the multi-configuration Ehrenfest method, here the energy transfer between these two dendrimers was also studied. And I think you will agree with me that these systems are rather large. But what I want to show you now is that this representation using the adiabatic state has problems, and I think you already know about it. But what you may not know is how a simple change in the parametrization can solve these problems. And the first problem I want to show you here is the singularity of many terms in the molecular Hamiltonian in the adiabatic representation, and comes from this matrix here that here is represented for two states. It's the non-adiabatic coupling matrix. And all these terms comes from the fact that the nuclear kinetic energy acts on the electronic states that depend on a big R here, the nuclear coordinates. And off-diagonal terms here are in fact the non-adiabatic couplings that I already mentioned at the beginning of this talk. And yeah, they tend to infinity at the conical intersection, but they are not that big of problem because when you integrate them over the Gaussian basis for the nuclei, they give back finite number. So we can really do the simulation with including those terms. It doesn't really pose any problem. What is more problematic is this term, also called the diagonal Born-Oppenheimer correction. These are in fact the diagonal term here. And they also tend to infinity because they are divided by the energy, but squared this time. And since they are on the diagonal, they look like potential terms. So it's like if the wave packets, let's say after an excitation to the upper state, will go to the conical intersection, and then it will hit this infinite wall at the conical intersection. You may wonder what will be the dynamics of such a system with such a potential. But in fact, you cannot even include this term because integration over Gaussian functions gives infinities. So this term is non-integrable for Gaussians, and you can really not include it in your simulations. You really have to overlook it, and it's a necessary but completely arbitrary approximation that you cannot really control. The second difficulty that can appear in the adiabatic representation is related to the geometric phase that is attached to the electronic states. So just to give you words on what it is, it appears when you transport your solution of the electronic Schrödinger equation continuously around the conical intersection, and you come back at the very same position, then your wave function acquires a minus sign. So it means that there are two possible solutions at the very same nuclear geometry that are continuously connected, but they are different. And this type of functions are called double-valued functions. It's like if they are living on this Mobius strip. You go around once and you change the side, and you have to go around twice to recover the original state. But now what's the implication of the nuclear part? We know that the electronic state is double-valued, but the nuclear part is also double-valued because it's coming from the projection of the total wave function on the electronic adiabatic states. So in this integral, we have also double-valued quantities. And overlooking the geometric phase can lead to very wrong dynamics, as I studied. For example, in low energy dynamics, the wave packet can split, for example, and go around the conical intersection. Then it should acquire different phases, in fact, opposite phases, and then interfere destructively on the other side of the conical intersection. And so we would observe, for example, a nodal line in the density, in the nuclear density. And also it can prevent from population transfer or this type of stuff. So the role of geometric phase can be important in low energy dynamics, but also when you excite your system and it de-excites through the conical intersection. Here we also shown that not including geometric phase can really reduce the population transfer. In this case, we had a full population transfer with the exact simulation. When we remove the geometric phase, it can be divided by more than 2. So it's really problematic in some circumstances when you don't account for this geometric phase. And the problem here is that with our ansatz for the total wave function, the nuclear part is built as a linear combination of Gaussians. And these Gaussians are single valued functions. there is a way to reintroduce the double valuedness, but the price is that you will need to build some models for the system, and usually you want to avoid that for on-the-fly dynamics. So really here there is another necessary approximation that you cannot really control. The method that I am presenting here can solve both of these problems at once. First of all, you have to observe that both these problems are appearing because the electronic adiabatic state depend on the nuclear degrees of freedom. And if you remove that, you end up with diabatic states. And in fact, it's just a diabatization. And you get rid of all these problems I talked about. One way to do that very simply is to say that, in fact, the electronic states will not depend on the nuclear degrees of freedom, but will depend on something that resembles the nuclear degrees of freedom, but is the parameter. We'll see how it can help later. And this parameter here is the center of the Gaussian wave function. So we will have several electronic states that will be each attached to their own Gaussians. And the state will be, in fact, calculated or obtained, as an eigenstate of the electronic Hamiltonian at the Gaussian center. So it's locally adiabatic at the center, but everywhere else it's considered to be diabatic. And this is what, in fact, we call crude adiabatic states. Since this parameter is time dependent, these states are also time dependent, and that's why we call it moving crude adiabatic states, MCA. And it solves both of the problem, as I mentioned, that already the big R dependency is removed here. So we have single valued states, and therefore the nuclear part can be single valued without any problem. As for the singularities, we saw that the singularities were coming from the non-adiabatic matrix, non-adiabatic coupling matrix, sorry. And that was the result of the action of the nuclear kinetic energy on the electronic state, but here they don't depend on big R, so basically it gives 0. Another advantage of this approach is the following, is that it gets rid of potential energy surfaces. And the reason why this is interesting is the following. Along the dynamics, you want to evaluate a matrix element over this potential energy surface, but you don't know these potential energy surfaces in the whole space. And you can trace this problem to the fact that you don't solve this electronic Schrödinger equation in the entire nuclear coordinate space. You usually evaluate it only at the Gaussian center or maybe at saddle points. But then you have to calculate this type of integrals, where this integration over big R here runs over the entire space. Since you don't know the expression of the electronic state over the entire space, you need to rely on some approximations or models, like, for example, the saddle point approximation or the local harmonic approximation. With the new approach, the integrals that you have to calculate now involves these moving crude adiabatic states, and they don't depend on big R, so you can perfectly exchange the two integration here and integrate first on big R. So you get rid completely of potential energy surfaces here, and you can calculate everything exactly. It's just a Gaussian transform of the molecular Hamiltonian. Then, if you think about it even more, the electronic states are in fact obtained as a linear combination of product of Gaussians, and all this integral is just a multidimensional Gaussian integration that can be done numerically exactly. So no models are needed, and this approach, at least for the evaluation of the matrix elements, is exact. And I tested this approach on this small dimension model with one explicit electron, so that I really have to obtain either the adiabatic state or the moving crude adiabatic states by diagonalizing the electronic Hamiltonian. And there is also one free proton, so that we can look at some non-adiabatic dynamics. And in this model, it's actually quite nice that we have these conical intersections between the first excited and the second excited states. So we indeed can simulate non-adiabatic dynamics. So this is what I did. I placed the initial wave packet on the side of the conical intersection, and I let it evolve in time. And it first hits this conical intersection. And in this region, there are strong non-adiabatic couplings that allow the population to go from the upper state to the lower states. This is what we can see here when we go back to the adiabatic representation. which is a signature that indeed this approach can really simulate the non-adiabatic dynamics. And furthermore, I looked at the effect of the geometric phase in the adiabatic representation by observing the appearance of the nodal line in the nuclear wave packet here. So this is a signature that indeed the geometric phase would be accounted for if we go back to the adiabatic representation. And finally, for all the simulations, I didn't use any model. I did all the integrals of all the matrix elements exactly numerically. And the only remaining approximation would be the number of basis functions that I used, but I ensured that all these calculations were converged with respect to the basis size. As a summary, just for this method, just to repeat what I said, it avoids the singular terms, it automatically accounts for the geometric phase. We can use it to calculate exactly all the matrix elements. And here there is a nice possible interface with quantum chemistry packages, because all what we have to do is just Gaussian integration. And if we combine it with classical trajectories, we can even have this two-step solution of the Schrödinger equation, where we do first quantum classical trajectories in parallel, and then we will reconstruct the basis and solve the quantum dynamical problem in this time-dependent basis. And last point, maybe important one, is that to ensure that the basis is converged, for example, in terms of number of Gaussians, we can use an automatic expansion of this basis. So there are many ways to do that, but I've been working on one way that automatically expand the basis using a variational criteria. So it completely fits within the variational approach. Okay, so far I've been talking about low energy dynamics and how I could solve many of this representation problem for the electronic state using this MCA approach. And now I would like to show you how these ideas can be also useful for attochemistry. When we are interested in attochemistry, we have to give up on having only few electronic states, and now we have to deal with very dense manifold of electronic states. And the reason for that is because the initial ionizing pulse is very short. So let's say it's 1.5 femtosecond. The energy window for the excitation would be roughly 20 eV. And in this energy region here, we may have like dozens or hundreds of electronic states, depending on the molecular system. So here, the first idea is that we can get rid of the adiabatic states, because the first idea, the idea behind using adiabatic states was first to decrease the computational cost of the problem, because we are interested in the lowest electronic states. And therefore, we are using this minimization problem that leads to diagonalization of the electronic Hamiltonian. But since we are in high energy domain here, we don't need to minimize this energy, and we can just bypass this diagonalization. However, in order to have a well-represented electronic state, we would like this state to adapt along the dynamics, and then we want to make it time-dependent. So basically, we replace the big R dependence by a time dependence here. So here I just talked about the electronic state, but we shouldn't forget also about the nuclear degrees of freedom. In this very dense manifold of electronic state, we may have several electronic states that are crossing with many conical intersections. So first of all, you need electronic correlation to well represent all these interactions at the crossings or avoided crossings. And furthermore, you have strong couplings between electrons and nuclei. And finally, you, as I shown you already, for example, with geometric phase, you may have quantum effects or also in the nuclear wave packets. So we have to keep all that in mind and say that now we want a method that can account for all this correlation. And since I have a quantum dynamics background from the nuclei, the first method that came into my mind when I thought about that was the multi-configuration time-dependent Hartree method. And the idea behind MCTH is rather simple. It's based on the Stocker decomposition of tensors. And here I give an example for the two particles where we can represent this electronic wave function in tensor product basis here for two particles. And we have this matrix with two indices here that is represented by this rectangular matrix. If some of the coefficients here in this matrix are very close to 0, because maybe they are associated to configurations that are very high in energy or very low in energy, then we would like to just not account for them and maybe find a procedure to automatically remove them. One way to do that is maybe a singular value decomposition, and we end up with this much smaller A matrix that would contain the important values here. And then we have also these matrices here that would allow to go back to the original space. So now our wave function looks like this smaller matrix here, and here we have now time-dependent states. And each of these time-dependent states is represented as a linear combination of some time-independent primitive functions. If we account now for the antisymmetry of the wave function, we need to add the f to MCTDH. So it's basically MCTD R3FOC. And this is very similar to what time-dependent complete active space method is doing. But here I am advocating in the use of, for the use of MCTDH, because with MCTDH, you can have even more flexibility in the wave function. You can do MCTDH in cascade somehow. So I am giving an example here on the 4-particle systems, because this is when it starts to be interesting. And all that is called multi-layer MCTDH, and it uses the hierarchical Tucker decomposition this time. So here we would have a 4-index tensor to deal with. And if we want to avoid that, to reduce the dimensionality of the problem, we can still apply this MCTDH method on this representation. But now we would have time-dependent functions that are in fact for 2 particles, each of them. But we end with here a matrix that has only 2 indices. So there is a gain here apparently, but everything looks like it's hidden in these time-dependent functions. And each of these time-dependent functions should be representing the dynamics of 2 particles. So we need to use these 3-index tensors. They are this big part here. The 3-index tensors basically are these cuboids there and there. So with this systematic use of MCTDH recursively, we can change our problem from the need of 4-index tensors to only tensors with 2 or 3 indices. And this is where we can have a huge gain. And that can be done on 2 layers, like I shown here, but also on 3, 4, for many more particles. So it can lead really to very flexible wave functions that can be used to reduce the computational cost. Now we would like to add the antisymmetry to these wave functions. But since we have this separation that is kind of artificial between particles that should be identical, it's kind of difficult to just use Slater determinants maybe, or just second quantization when we are not in the Fock space, basically. So we have to move to the Fock space and use what we call the second quantized version of ML-MCTDH. And this was done very recently at the end of the last year. So I would like to use this approach for the electronic wave packets. But let's go back to the problem of the nuclei and also the correlation between the electron and the nuclei, because this is where it can get also a bit difficult. So we know that the nuclear wave packet should be quantum, but we know that it's also slowly evolving on the timescale that we are interested in. So we can think that the wave packet will remain rather localized, and we can use MCTDH quite efficiently to represent these wave packets. For the electron-nuclear correlation, we have to think about a way to hard-code this correlation in the basis. And this is usually done by the fact that the electronic basis, for example, atomic orbitals, are attached to the nuclei. So they will depend on the nuclear coordinates here, which means that our electronic states are not only time dependent, but they are also parameterized by the nuclear coordinates. And then we go back to this problem that we have these large dimensional grids if we want really to represent this electronic state in the whole space. So we go back to the curse of the dimensionality with problem for the wave function expansion and numerical integration. Furthermore, the action of the nuclear kinetic energy on the basis leads to second derivatives. But here it's not that much of a problem as for the adiabatic states because they don't go to infinity. How what I've been doing for low energy dynamics can help. So it does it in the following way. First, we use Gaussian trajectories because we need it for applying the MCA trick. And this would work because the wave packet is rather localized in the nuclear space. And then we apply this trick that we replace the nuclear degrees of freedom that parameterize the electronic states by the parameter that is the center of the Gaussian. So it really, again, connects this electronic state to the corresponding Gaussian. And by doing so, we avoid the dependence on nuclear degrees of freedom in the electronic state. And we remove, for example, the second derivative. We also simplify all these integrals, again, because this is just one multidimensional Gaussian integration. Okay, so this is actually very recent work, and I will stop my presentation here with the perspectives. I would like just to remind you that this exact version of MCA would lead to a method where only the finite basis approximation, where only the finiteness of the basis is the approximation, because all the matrix elements will be exactly obtained. But all this matrix element needs to be implemented first. And there are many new of these integrals. So this is a huge work that we are going through right now. But the good thing is that once you have this method that is implemented, you can use that to devise approximations for all these integrals in a very controlled manner because you have the exact result at this position. Then there is also the fact that you can reuse all the integrals on the primitive basis for MCTDHF. So all this work would be transposable directly to the simulation of attosecond processes. And we can reuse all this machinery that was developed in quantum chemistry packages. We just need to interface it. And finally, I talked about the automatic expansion of the basis, and this can also be done for the electronic part. This is actually coming from a paper, very recent, by Hans-Dieter Meyer. So I encourage you also, if you're interested in that, to look at this paper. And I would like now to thank my collaborator at University Gustav Eiffel, Alexander Mitrushenkov, and also my newly arrived PhD student, Rosa Maskry, that will work on this project. I also would like to thank the people in Toronto for collaboration on MCA and also the work I've been doing with them on geometric phase. So Archer Ismailov, Mina Assad, and Ilya Ryabinkin. And finally, I would like to thank Fabien Gatti from Université Paris-Saclay because I'm collaborating with him on these developments, including MCTDH. And I would like to thank you also for your attention.
Thank you very much, Loic, for this very detailed and pedagogic presentation. So now we have time for questions, and I see already one hand has been raised. Eva, you raised your hand. I think you wanted to ask a question.
I just wanted to clap my hands.
Okay.
Thanking for the nice talk.
Okay. So it was not a question.
No.
Okay. Are there questions? Let me check the list of to see if there are hands over here. Morgan Vacher, please ask your question.
Yes, can you hear me fine?
Yeah.
Yes, okay, no, thank you, Loic, for this very nice talk. I just had a question about this automatic expansion of the basis. I mean, maybe you mentioned it, but maybe I missed it. Can you say a bit more about it? I mean, you insisted on the fact that it was automatic, but I'm guessing you must have some threshold that you choose.
Yeah,
no?
You need the threshold. So this must be benchmarked, of course. So more work needs to be done in this direction. Maybe I can say a few more words for the context for the people, if they are not familiar with that. So there are automatic expansion like multiple spawning. Also, there is the cloning technique. But all these methods rely on criteria that are only applied on the local basis, basically. It doesn't account for the fact that there is a bunch of Gaussians that are around. With this new criteria that I call it variational, it basically uses all that to make sure that we are not creating a new basis when it's not necessary. And basically the same work was done by David Mendiv, Tapia, and Hans-Dieter Meyer, but they did that in general for multi-layer MCTDH. And it's also variational. So just if I can give more context.
Okay, so there's a difference in your approach that you take into account that there may be other bases around.
Yeah.
Can already pick up some population,
Exactly.
but you still have some threshold to
you need that.
Yes.
So if you don't design the threshold optimally, I would say you may over expand. Way more bases than what you actually need. If you don't do, if you can also do the opposite way, like if it's not sufficient, you will not converge fast enough, and you may have to restart your calculation. So it's very tricky still. But this is like a bunch of tools that we have at our disposal, and now we can act on the automatic expansion at the level of the quantum classical trajectories, let's say with the multiple spawning or the multi-configuration RNFS with the cloning. They are doing that already, but we can also do it for the solution of the quantum equation. I mean the Schrödinger equation. So it's on the level of the coefficients this time. So we can play on both. Maybe we can overspawn, but if we have a lot of trajectories in parallel, it's not really that of a problem. And then we can like take what are the ones that are really important among all this, I would say, ensemble of trajectories that we have using the variational criteria that was derived here. If it makes sense what I'm saying.
Yeah, thank you.
Yeah, welcome.
Okay, there is a question from Graham Worth. Please, Graham, open your microphone.
Hi there, can you hear me?
Yes.
Yeah. Hi, Loic. Yeah, you've certainly looks like you're going to be taking on quite a large amount of work to keep you busy for the next few years.
Yeah.
Yeah, I just have a question, a bit on the sort of the basis of the MCA method that you're doing.
Yeah.
Because to me, it's related to, the exact factorization method of Hardy-Gross and Federica Agostini.
I mean, there are always connections, but
yes, but what I was wondering there was,
indicate me exactly what you think about.
Well, I mean, it's the fact that your expansion. So you're expanding. You now have you basically have if you like, your time-dependent electronic wave function, which is sort of following. So you're sort of getting like almost an Ehrenfest type surface, yes, because you could sum over those and you basically get the same ansatz. But what I was wondering there was, so in the exact factorization method, because they have the coupling between the nuclear and the electronic parts, it looks much the same. And you then effectively have a non-adiabatic coupling that's experienced by the electronic part that they then, in their sort of to make it useful, throw away. Are you having to do something similar, or are you really including, you still have absolutely everything?
No, I have absolutely everything. So maybe I'm not sure which term exactly you are thinking about, because I don't have all the equations in mind. I'm not an expert of exact factorization, but I can ensure you that here everything is included. No terms are throwing out for some reason. There are non-adiabatic couplings that appear along the trajectory only. So I am accounting for them, and it's because I have this time dependence here. If I can come back here, I have this time dependence here to account for. That is basically time derivative of the basis, and that naturally leads to the velocity scalar product with the non-adiabatic coupling, if you see what I mean.
No, sure. Yeah, but that's in the nuclear part.
But this is the only place where the non-adiabatic coupling appears.
Okay. I'll have to look at that, because I would assume that in the electronic part you must have terms that are related, like in an Ehrenfest type approach, because you've got that coupling. There'll be terms driving the electrons from the nuclear momenta, no, as well.
Yeah. The only difference is like the multi-configuration Ehrenfest method that was developed is still relying on the adiabatic representation to re-expand the wave packet. Maybe there is like an intermediate diabatization, but still the initial form is the adiabatic representation. And here we just bypass it completely by going directly to this moving crude adiabatic representation. So you can think that maybe the result would be the same, but the way is much like shorter to reach this point. And on the way, you are not dealing with all this diabatization or approximation of the matrix elements and all these things.
Okay, yeah. Thank you, Loic. Thank you.
No, you're welcome.
Well, I think we should move on. So thank you, Loic, again for the presentation and for the discussion.
Thank you.
So we move to the third speaker of this session, Elke Vashauer from Aarhus University, and she will speak about Fano meets nuclei, how nuclear degrees of freedom influence time-resolved spectroscopy of electronic decay processes. So Elke, please.
Hello. And I would also like to thank the organizers for giving me the opportunity to present my work. And let me share the screen. Do you have the presentation now?
Yes.
Excellent, thank you. Well, we are obviously coming from very different backgrounds, but what we are all interested in is basically what happens during a chemical reaction and how can we monitor that. And in order to do that, we obviously need short pulses. But as you can see from this pulse, well, the pulse is limited by the frequency of the mean photon energy, because we cannot put less than one full cycle in our pulse. And that means that we have reasonably high energies if we want to go to very short pulses of several electron volts, well, many electron volts. And when these interact with the system, we create ionizations or excitations from inner shells of these atoms or molecules. And if we want to extract time-dependent information from that, well, we first look at what happens if we do that in the first place. They can decay, these systems can decay via electronic decay processes. And the best known of these is probably the Auger-Meitner process, where you ionize from an inner shell, you fill the vacancy with an electron from a different shell, transfer the energy to a third electron, which you then emit, and you end up with a doubly charged unit and an electron. But there's also a different class of electronic decay processes where you ionize from the inner shell from one unit, you fill the vacancy with an electron from the same unit, and you transfer the energy to a second unit, which then gets ionized. So you end up with two singly positively charged units that repel each other and undergo Coulomb explosion. This is the interatomic Coulombic decay process. What they have in common is that you have a rearrangement of your electronic structure and the emission of one electron. And we are going to have a closer look at the spectrum that you get from this electron. How do we, as theoreticians, get from this picturesque representation to a time-resolved spectrum? Well, let's start with the time-independent perspective. Hugo Fano proposed a theory where he described the wave function, the total wave function of the system, as a superposition of bound-like states that we have, that we call R, and continuum states. And he didn't specify these wave functions further than saying that these are eigenstates of a common Hamiltonian. When we then take our system in the ground state here at the bottom left, and we take a pulse with the mean photon energy of omega, we excite to the resonance state. This then couples to the continuum and decays under emission of an electron. Alternatively, we can also use the pulse to directly go to our final state that includes a free electron. The interference of these different pathways then gives us a very characteristic line shape, the so-called Fano profile, which is characterized by a parameter Q, which is basically the ratio between the excitation probability to the resonance state versus the transition to the continuum state. And you see, well, depending on this Q parameter, you get different minima, different maxima, and you get different peak intensities. What we can also construct from this theory is the decay with gamma, which is given by the sum over the different decay channels of the absolute square of this matrix element. So we have a very effective description without actually necessarily considering what these functions are. Well, let's look at the time-dependent perspective of it. Theoretical and experimental approaches have been able to both describe and measure the buildup of this Fano profile in time. And if you wonder, these two experimental papers or collaborative papers from 2016 were really published back to back in the same journal. And I'm going to show you that we, with our theory, get exactly the same shape. How do we do that? Well, the property we're interested in is the time and energy differential ionization probability, P, that we have here. This basically gives us the probability to measure an electron of a certain kinetic energy at a specific point in time. Well, then we want to know the amplitudes here, and for this we need this the time-dependent Schrödinger equation to get our time-dependent wave function. Well, we solve the time-dependent Schrödinger equation by using first-order time-dependent perturbation theory, and very important, we here assume that our pulse intensity is low enough that we can still use the dipole approximation. When we do that, we get an expression for this amplitude up here that looks like that. What you can see is that we have three different terms. The direct term that I already described, the resonant term that I already showed at the beginning, and the indirect term. And we can understand what this indirect term is by reading from the right. So we start in our ground state G. We excite with our laser pulse to a continuum state. The continuum state evolves in time and couples to the resonance state, which then decays under emission of an electron. The interference of these three components then gives us the time-resolved Fano profile. We proposed an experiment last year, and for a different system, but very similarly, this was performed at the end of last year experimentally. So we start not with an ionization, but with an initial excitation. We fill the vacancy with an electron from the same unit, transfer the energy to a second unit, which then emits an electron. And this electron has an energy of roughly 5.3 electron volts. And as you can see, we have this very nice Fano profile. What we then also do, if we want to measure this, actually, you come with a second pulse. This is not supposed to be a strong field ionization, but rather a near infrared pulse. We can use this pulse to remove this excited electron. And then we have the initial state of the ICD process, which then occurs and emits an electron of a different energy. But most important, it's a lower energy, which means we can, by using different time intervals, create and measure this time result Fano profile. But we are having analytical effective functions. That means we can look at the basic properties without introducing any numerical or experimental errors. I mean, we have some assumptions, but we can look at the basic properties. And the first thing is at large times t. So basically after the decay happened. And what we see here in the solid lines is that we get the Fano profile, but not only the Fano profile, but the Fano profile folded with a Gaussian function, which is the Fourier transform of the time envelope of our laser pulse. That means that the shorter the pulse is, so the lower the number of cycles in our pulse, the broader becomes the overall peak. What we can also see in this dashed line here is if we don't excite on resonance. So here I've taken a system with a different resonant energy. Then these two functions don't have their maximum at the same place. And that means that we basically damp this Fano profile. After shorter times t, we can look at different values of Q. And what we see is the larger Q is, the smaller is the system. The larger Q is, the less pronounced is also the Fano profile, because the larger Q becomes, the more this Fano profile evolves into a Lorentzian. You can see that from the interference terms and the relative contributions to the overall signal. But what you also see at smaller times t is this oscillation in energy. And this oscillation in energy we can analytically see, and it's proportional to this cosine function down here. But what you can see from this equation is that there is not only an oscillation in energy, but also an oscillation in time. And indeed, that's what we find. This oscillation decreases over time. And we can analytically see that we have different terms that decrease with different exponential functions. So we have both this exponential function of minus t over tau, and we have the different exponential functions minus t over 2 tau. This first function will probably be dominant in the beginning and then be more or less decayed at larger times, whereas the second one here is dominant for the decay at larger times. But still, if we fit a function, and I've done that here for all maxima starting from the one after 300 femtoseconds, you will always underestimate the lifetime of your system, because you always will have a part that comes from the other term. And it's not only me who's observed that, But we've also seen that in this work for the autoionization of helium. Here, the theoretical lifetime was 17 femtoseconds, but from the fit, they extracted 12 femtoseconds. Now, well, I've talked a lot about atoms, but what we're really interested in is molecules. So let's start with a dimer. When we look at the dimer, we can have our pulse with a mean photon energy omega, which I have chosen to be the 0-0 transition energy. I mean, I use model potential, so I can do that. But because I have a very broad laser pulse, I coherently excite several vibrational or nuclear resonance states. And these can then decay to all the final states that are energetically accessible. Alternatively, we can go to the final state directly and emit an electron with a certain kinetic energy. And the question is, how can we describe this theoretically? Well, we can in principle make the same ansatz, but we need the nuclear degrees of freedom. To be fair, Fano never restricted these wave functions to be only electronic, but let's try to disentangle this and explicitly formulate a product function of one resonance state and all bound nuclear states that this potential can accomplish. So here we have the bound state or the vibrational state of the resonance state, and here we have the vibrational eigenfunctions of the final state. In order to proceed with that, we need to determine these coefficients A lambda and B. And if we do that, well, we figure out that this is not as easy as one would have wished for. So we make a couple of approximations. One is that we use the Born-Oppenheimer approximation. So we cannot describe conical intersections, as we just heard in the talk before. And for the moment, we are restricting ourselves to cases where the resonance states do not couple via the continuum. And if we do that, we get an effective decay width for each and every resonant state, where we basically weigh our electronic coupling parameters with the nuclear wave functions and take the absolute square. And we get these lengthy coefficients, which I won't discuss in more detail at the moment. Well, let's have a closer look at these effective decay widths. Well, usually you would either calculate the decay width of a system for different places in R or different geometries, or just the equilibrium geometry. And then if you wanted to get more accurate numbers, you would perform a dynamic simulation. But I haven't tested this formulation yet, but it looks very promising that there is an easier way to go further to get these decay widths. And of course, for different systems like the ICD, we would have 1/R⁶ dependence of the decay width, or for the OJ, we would probably have a proportionality that is exponential. But for this study, I will assume that the decay width is independent of the geometry. So let's go back to our time-dependent formulation. We again look at the amplitude. And what we see here is that we again have a direct, a resonant, and an indirect term, but we have this innocent looking sums at the beginning of the resonant and the indirect term. And that means that we can have many channels, and the contributions to the wave function can interfere to get the signal in the end. What I would like you to focus on now is that we have these extra terms. So we have an overlap term for the resonant state and the nuclear final state. And if we make the Condon approximation and take out this dipole matrix element, we also get a Frank-Condon factor here from the nuclear ground state into the nuclear resonant state. And here are some examples. I've used model potentials, Morse potentials with equal minimum distances, and I would like to show you some basic properties. Here on the left, you have the case of one bound resonant state and two bound final states. And what you see is you have two peaks, one here at 10 eV, that's the 0-0 transition. For all the spectra, the 0-0 transition is chosen to appear at 10 eV of kinetic energy. And then you have a second peak down here. And let's compare it to the other one that is similar, which is for two bound states in the resonant state and one vibrational final state, where you also have the peak, the two peaks, one at 10 and one at a higher energy. And what you see is that you will get a rather complex structure here, which almost looks like an interference structure. But from the analytical formulation, we can see that this is not an interference pattern. This is just overlapping interference signals, because of course each of them is a final profile, which is an interference signal, but these are not interfering with each other. If we now look at the case over here to the right, I've chosen the two bound states of the resonant state to be so close together that you cannot distinguish them. And what you see is, well, the final profile is a bit blurry. And well, if you wanted to get the energy difference of these two vibrational states, you could in principle think, well, we have, if we look here, we basically have an interference between two resonant states. And from this, we can get the energy difference. But the beating of the interference spectra will give you exactly the same frequency. But what you can do is basically go look at a different energy than the maximum, analyze the frequencies by Fourier transforming, and then you will get the energy difference. If we look at the energies, we can also look at two different cases. So on the left here, we see the case where different numbers of bound vibrational states and one specific final state. You again see here that you have one principal peak and then you have one peak, the 0-0 transition at the maximum, and then you have the other peaks along this curve, which are damped. What you also see, especially if you look at the orange curve, where you have many resonant states, you see that these are not, these don't have the same amplitudes. Also not if you consider the damping that is already included. And this is caused by the overlap integrals that I showed you. Because the overlap integrals between the different vibrational states, well, they are just completely different. But that also means that you get different effective Q values for each of these different peaks. That also means that if you shift the potentials relative to each other, each shift will give you a new effective Q number, and you can close and open channels by just moving the potentials without changing the energies. Then let's have a look at the right. Here we have one vibrational resonance state and different numbers of final states, nuclear final states. And here we don't see this pronounced Gaussian function. And the reason is that we have different numbers of final states. And each final state gives rise to a new function, which means that we effectively broaden our peak. And then there's another thing that is very nice that we can see here, is that these overlap integrals, they don't necessarily have to be positive. And if one of them is negative, we can basically flip the peak that you see here. So, to conclude, it seems I have a lot of time left, but well, we have a higher number of resonant and final states than in pure electronic description at a reasonably small energy interval, which is clear because we are dealing with molecules. Then the overlap integrals weigh all the different contributions individually, and we get different effective Q parameters, which changes the line shape. Also, if we move the potential energy surfaces with respect to each other, we can open and close channels by affecting the overlap integrals. Because we have been very clear in what approximations we included, that means that basic properties that will be seen in experiment or are seen in experiment can be analyzed and be attributed to exactly these approximations and thereby the physical effects that cause them. And what we see is that, I've proposed a new way to correct the purely electronic decay width to include the nuclear effect of the wave function. And there are, of course, a couple of people that have contributed, and here I just mentioned the very few. So this is Lars Boyer-Messen, Mats Zimmermacher, who contributed with some calculations, and Marcel Mudrich and Christian Ott for some very helpful discussions. And now I'm looking forward to your questions.
Thank you very much, Elke, for this nice presentation, also for the pedagogy. There is already a hand. Yeah, Alicia Palacios, please ask your question.
Hi, very nice talk, very well explained. Thank you, but I have just a couple of questions. Well, one is more a remark, because you keep pointing out this Gaussian shape form, because you're looking at probabilities. But if you look at, you define an effective cross-section, they shouldn't depend at all on the pulse duration. I mean, in the long time limit, the profiles they are plotting, they should look the same, exactly the same. In the one, this is a one photon process, no matter if you have a delay happening after. So that was the comment. And the question is, did you use model potentials, but I'm wondering, did you take into account the change of the nuclear mass? Because if you go to lighter and lighter atoms, you will see that these Fano profiles disappear. And as you go to heavier and heavier atoms, these Fano profiles are sharper. So did you take into account this, or any comment about it?
I didn't include the effect of the mass yet. These are really just model potentials, but that's a very interesting aspect to look at, because I mean, that's very easy to include.
Yeah, I mean, we have some work on that. I mean, we can discuss later, because
that would be really nice.
I'm curious to know in this model. Well, this it's a model, but it's quite a complex model, and I'm pretty sure you will have this effect.
That would be nice.
Okay, thank you.
Okay, more questions? I don't see. I have also. I think. Could you show again the slide in which your ansat, your extended Fano ansat, in which you include the nuclear wave functions?
Yes.
Because I have problems to digest that this can be. I mean, you say that this is Bohr-Oppenheimer. This is not Bohr-Oppenheimer, because you are. I mean, your psi E there, you know, contains different nuclear wave functions multiplying the different electronic components. So, strictly speaking, you are not factorizing the electronic part and the nuclear part. So I wouldn't call this Bohr-Oppenheimer approximation. I don't know. You would agree with this? I mean, your wave function has, like, let's say, grosso modo, 2 electronic components. Okay, and each one is multiplied by a different nuclear wave function. So, which means that, well, this is not the Bohr-Oppenheimer approximation. So it's just a matter of language, or would you agree with this?
I'm not entirely sure that I understood your point yet. What I can see is that obviously, contrary to the one above, the original ansatz, the wave functions don't all have the same energy, but there is also a formulation where that's not the case. Could you? So why do you again think that this is not a Bohr-Oppenheimer approximation?
Usually, well, people call Bohr-Oppenheimer approximation to when you write a wave function as a product of an electronic wave function and a nuclear wave function.
Yes.
But here you don't have. This is more complicated than that. I mean, you have an expansion over electronic states, a limited number of them, of course, because it's the final ansatz. Okay?
Yes.
And each one is multiplied by a nuclear wave function. So in some way, this expression is very similar to the one we saw in the previous talk. Okay, in which every electronic state was multiplied by, you know, a nuclear wave function.
That's true. Yes.
So in this sense, this goes beyond the normal Bohr-Oppenheimer approximation. So maybe what you mean by Bohr-Oppenheimer is that you are neglecting in the equations that you write down later, you are probably neglecting non-adiabatic effects, as you said. So,
yes.
So you are, let's say,
okay, yeah,
you are in some way an adiabatic picture. You are using an adiabatic picture, but you are not writing the wave function as a product of an electronic and nuclear wave function. You are going beyond that.
That's true, yes.
So I think it's just a matter of language, but I think it's important. And I see a hand from Nicolas Sisourin, please.
Just before that, what would you call it?
Well, I mean, I don't know. I wouldn't call it Oppenheimer. I would, you know, it's call it as you want, but it's not
Okay, so I have a child to be named.
Yeah. No. Anyway, this was just a comment, and I see that there is a question by Nicolas.
Okay.
Hello, can you hear me?
Yes.
Okay, great. Just on your comment, Fernando, I think you're right. And in the context of Fano, this adiabatic approximation, they call it local approximation.
Yeah.
So I think that's right. It's in the later equation when you plug this wave function into the Schrödinger equation and so on, then you neglect some interaction. I mean, some terms which are this adiabatic approximation, but we call it local approximation in this context. I have also a question about, towards the end of the presentation, Elke, you show the case where the two vibrational resonance, they overlap each other. But I think then, isn't it that your ansatz rely on the fact that they should be non-interacting?
Yes, the ansatz relies on the fact that they are non-interacting. But I mean, you can still have energy differences that are that small that you cannot resolve it in the spectrum.
So, but the question is, does it, make sense to talk about just two states? The whole theory should maybe break down, or you have to add something else. I'm just wondering.
I've of course included, not included the coupling via the continuum, but what is the problem with having several states that lie so close together that you cannot resolve them in experiment?
No, it's not the problem of the experiment. It's the problem of the ansatz. If you start your equation saying that you should have only non-overlapping resonances, and then you take this limit case where they do overlap, then my question is, how correct is that?
That's a good question. Well, this is probably not the most correct way to do it. I will have a look at that. But that, as I already said, that's probably not the correct way, exactly the correct way to do it. But that's the approximation that I chose in order to get the first numbers and the first spectra. So this is, of course, what I'm going to look at later.
Okay, thanks.
Okay, I don't see any further question or comment. So I think, first I'd like to thank Elke again for the presentation and for the discussion. And then I think we can close the session almost in time. So I thank all the speakers for keeping the time strict. And so we resume the meeting at 1:30 Central European Time. And in the meantime, you can have lunch, but you can also meet the speakers in the links that are indicated in the Attochem website. So if there are further discussions, questions, comments you want to make, this is a great place to do it. So thank you, all of you, for attending the talks, and see you at 1:30.